Hello, today we are going to talk about a very interesting topic in classical mechanics that is known as rigid bodies. And we are going to start by defining what a rigid body is. So just imagine that we have an object that is made of particles, okay? These particles, well, they are separated each other with certain distance, okay? And well, this distance will be constant in all the motion of the rigid body. Okay, this rigid body is moving. Okay, but the distance between the particles that compose the rigid body is always going to be a constant. It is not going to change during the motion of the object. Okay, this is the main idea about a rigid body. Okay, so it will be important to define two coordinate systems on the rigid body. One is going to be like the normal one that we know, the one that is composed with an orthonormal basis. For example, like this, x, y. Okay, so we can locate any point of the rigid body with a vector r, for example. And then we are going to define another coordinate system that will be, for example, maybe like this. Okay. Again, I think there is no need to mention that all the vectors that compose this coordinate system are always going to be orthonormal. Okay, but this coordinate system will be like named with the prime notation, x prime and y prime, just to remember that it's a different coordinate system. But the important thing here is that, well, this coordinate system will always be fixed in the rigid body, okay? On the other hand, the original coordinate system, or let's call the natural coordinate system that I draw in green, the natural coordinate system. This is just the name that I choose to give to this coordinate system. It's not like it is known as the natural coordinate system. But the thing here is that when the rigid body is moving, well, this coordinate system will stay here in this position, but the orange coordinate system, the prime coordinate system, will be moving with the rigid body, okay? Because it is fixed to the rigid body, okay? Perfect. This will be very, very important for what we want to explain here. So if we are talking about rigid bodies, we may be wondering what happens with the energy of the rigid body. Well, again, we can ask about two types of energies of the body, but in this case we are going to start with the kinetic energy. What happens with that kinetic energy? How can we express the kinetic energy of a rigid body in a very rigorous way? Well, first of all, again, like I did in this coordinate system, in this natural coordinate system, we can also define a vector for the orange coordinate system, which is going to be the vector r again, but it will have different components. You know that, for example, for r in the coordinate system green, we will have the components, for example, let's call it x1, e1, where e1 is a unit vector, of course, plus x2, e2, plus x3, e3. And again, looking that we have the same vector r located in a point on the rigid body. On the other coordinate system, we can express this position, for example, with the coordinates x1 prime, e1 prime, plus x2 prime, e2 prime, plus x3 prime, e3 prime. Of course, this needs to be the same because we are locating the same point on the rigid body. Okay, as you should know, well, if you have already taken some courses of linear algebra, you should know that we can relate two orthonormal bases with a matrix that is the transformation matrix. And well, we can represent an equation that relates to well, the two bases like this. For example, the I component prime will be equal to some constant that we will call aj I prime ej. Okay, in this case, and these quantities will be able to change on time. And look, that what we are doing here is to transform a vector on the basis, on the natural basis, to the prime basis. Okay, and well, if we want to express what is the transformation matrix, you know that we can write it as, for example, a1 1 prime, a1 2 prime, a1 3 prime, and let me make a pause to complete this matrix. You see what's the way we are going. Okay, and just if you don't remember maybe your linear algebra courses, this is just like expressing the prime basis in terms of the other basis, and these elements represent the components of this vector in terms of the natural basis that we defined. And there can be many different transformation matrices. In this case, we will be interested in a particular one that is known as the rotation matrix. So let me draw again the rigid body here, for example, and let me write the coordinate system here. What happens if we have another coordinate system, for example, like this, that is rotated on a certain angle phi? Well, we know that these can be represented with a rotation matrix that, well, for now we are not going to show why this matrix has the next form. It is very known that the rotation matrix for this case is given by this matrix that I'm writing over here. Sine phi, cosine of phi, 0, 0, 0, 1. Okay. Another important thing is that you can see that this matrix has, well, order of 3, but in this case I didn't draw the z-axis, okay, but you need to know that we are working in 3 dimensions, okay. Maybe it's not necessary to draw the z-axis, but you can see here that the r vector has 3 components, one for each axis. Okay, perfect. So right now we are going to show some relations that will be very useful to define the kinetic energy of the rigid body. So we know that looking at the bases are orthonormal, we will have, for example, that the Kronecker delta I prime j prime will be equal to ai prime dot e j prime. Okay, but we know that e I prime is equal to I, let's use the index k here, I prime e k dot a l j prime e l. Okay, I'm just using this relation that we have here to express the dot product between these two quantities and take that equal to the Kronecker delta. Perfect. So again, we see that we have again a dot product of orthonormal vectors. So that will be a Kronecker delta again. So this is going to be equal to a ki prime a l j prime Kronecker delta kl. Perfect. So that means that, well, if we use this Kronecker delta with this term over here, the L is going to become a K. So this will be equal to AKI prime, AKJ prime. And again, this is equal to the Kronecker delta I prime, J prime. Very important relation that we are going to use later on. Okay, but look that, well, what we have here is a product of elements of some matrices. Look that, for example, if this term will be a I k prime, we will have like the the same matrix that we have here, but just a different element. But look that what we have here is, well, the same element, but with the indices exchanged. Okay, so that means that this element represents the transpose matrix of the matrix that represents this element. Okay, something like this. Okay, but what we have is that the product of the transpose of A times A is equal to a Kronecker delta. So that means that in matrix notation we will have that A T times A is equal to the identity matrix that allows us to conclude that A is an orthogonal matrix, because we see here that the transpose of A is equal to the inverse of A. That's why A is an orthogonal matrix. Okay, so looking at any matrix commutes with its inverse, we can establish a similar relation to this one, but we can just switch the prime notation to take the next. The Kronecker delta ij is equal to aik prime ajk prime. Okay, it's like just the same, but switching the order of the prime notation. Okay, perfect. So what are we going to do now is the next. We are going to assume that the rigid body is made of n particles. Okay, so that means that we are going to have an r vector for each particle. Okay, so we can define that r vector as r sub alpha, and we can express this as xi alpha ei equals to xi prime alpha ei prime. Okay, let me explain. This alpha vector corresponds to the alpha particle that compose the rigid body. Let's say that this is the particle alpha. Okay, in this case alpha is going from 1 to n. Okay, the n is the total number of particles that compose the rigid body, and here we are expressing the r vector in terms of the components in the natural coordinate system, and here in the prime coordinate system. Remember that this is fixed to the rigid body, so that means that these coordinates are not going to change in time, because, well, the coordinate system is moving with the rigid body, so that means that the position of the particles that compose the rigid body with respect to the prime coordinate system are not going to change. Okay? And on the other hand, these components are actually going to change on time. Okay, perfect. So we can relate the components of the vector in one basis with the components of the other basis with the next equations. We are going to have that the I component of the alpha vector is going to be related with a component of the transformation matrix aij prime times xj prime. Okay, on the other hand, xi prime for the alpha vector is going to be equal to aji prime xj alpha. Again, we are taking a component with the prime basis and we are multiplying it by some term that will allow us to take that component through the natural coordinate system. Okay? So, and this will be like the inverse operation. Okay, perfect. So what happens if we substitute this quantity in this component over here? Well, we are going to get that R alpha is going to be equal to A I j prime x j prime E I. Okay, in this case, just for convenience, if you want to check the book that I'm using to study this, the book changes the j for the I, so let me just rewrite. Actually, you know that there is no difference, okay? It is exactly the same. Okay, we are just switching the indices. Perfect, and again, remember that this component is for the alpha vector. Okay, so we are interested in finding, well, the velocity, looking that we are interested in the kinetic energy of the rigid body. So that means that our alpha dot is going to be equal to, well, the derivative with respect to time of this quantity. But again, remember that the components in the prime basis doesn't change because the coordinate system primed is fixed to the rigid body. So that means that the only quantity that changes on time is this one over here. So we can express that as ji prime dot xi prime alpha ej. Okay, perfect. Okay, so now we have the velocity of the alpha particle of the rigid body. If we want to find what is the kinetic energy of the rigid body, well, we need to sum the kinetic energy of each particle that compose the rigid body. So that means that, well, the kinetic energy of this particle, well, of course, is going to be 1/2 the mass of the alpha particle, of course, r dot alpha. Okay, so then the total kinetic energy of the rigid body is going to be the sum of all kinetic energies. So it will be the sum from alpha equals to 1 up to n of 1/2 m sub alpha r sub alpha dot r sub alpha dot. Look that when we substitute this velocity that we found, we will have a ej dot ek, for example. We will have the dot product between components of the orthonormal basis that we defined, and the dot product of an orthonormal basis will be equal to 1 if they are equal, or equal to 0 if they are different. Okay, so the point here is that those terms are going to disappear, and this will be equal to the sum from alpha equals to 1 up to n of 1/2 m sub alpha times a j I prime dot, of course, xi prime alpha times a dot j k prime x k prime alpha. And well, let me write that better, in a better way. This will be like the kinetic energy is going to be equal to, and we are going to take these elements out of the sum, so it will be aj I prime dot aj prime dot, the sum from alpha equals to 1 up to n of 1/2 m sub alpha xi prime alpha xk prime alpha. Perfect. So right now we have just found an expression to calculate the kinetic energy of the rigid body. Okay, perfect. Well, by now we haven't introduced yet what is the inertia tensor to express the kinetic energy of the rigid body. So we still have a lot of work to do. Okay, but what we are going to do now is to introduce some relations to be able to develop the inertia tensor definition. Okay, what we are going to do now is to use this expression over here. We are going to take the derivative with respect to time on both sides of the equation and to see what happens. Let me establish first that the Kronecker delta I prime j prime is equal to aki prime akj prime, and if we take the derivative with respect to time, well, looking that the Kronecker delta is a constant, that will be 0, and here we are going to have, well, the product rule for derivatives. It will be something like this. Here we have a dot, and then plus aki prime akj prime dot. Okay, so this leads us to aki dot I prime akj prime equals negative akj prime dot times aki prime. Okay, here and notice that I switched the order of the product in these two quantities. that can be made because, well, these are just real valued functions that depend on t. So we have this relation again. But the important thing here to notice is that this equation tells us that the product of a dot ki prime a kj prime is antisymmetric in the indices ij. Okay, so looking that this product is antisymmetric, we can establish a relation with the Levi-Civita tensor that will tells us that aki prime dot times akj prime is equal to the Levi-Civita tensor I prime j prime s prime omega s prime. Okay, and for the ones that do not know what is the Levi-Civita tensor, let me define on a quick way. We will have this. This is going to be equal to 1 if the indices represent an even permutation of 1, 2, and 3. Okay? It will be equal to -1 if, again, these indices are an odd permutation of 1, 2, and 3. Okay, and 0 otherwise. This means that, for example, if we have E1, 1, 2, this will be equal to 0 because we are duplicating the number 1. Okay, if again, if we have the number 2 twice, again, this will be equal to 0. And the same thing happens with the number 3. Okay, perfect. So this will be the definition of the Levi-Civita tensor that is actually on the book that I'm using to explain this topic. Okay, and I will write on the description of the video the name of the book. Another thing that you need to know is that, well, the Levi-Civita symbol is invariant under cyclic permutations. That means that, for example, if we have the order 1, 2, 3, well, it will be the same as having 3, 1, 2, and the same as 2, 3, 1. Okay? So look that we have an ascending order from the left to the right. We are going to have 1, 2, 3. For example, if we have 1, 3, 2, well, in this case, this will represent that the Levi-Civita symbol will value -1. Okay, because we are not respecting the order from the shortest number, which is the 1, to the largest number, which is the 3. Okay, perfect. Okay, another equation that we are going to use that relates the Levi-Civita symbol with the Kronecker delta is going to be the next. We will have that E, or epsilon actually, I prime, j prime, k prime, E, I prime, L prime, M prime is going to be equal to the Kronecker delta, j prime, L prime, delta. And for now, I'm going to stop saying prime to express the indices because I think it's not necessary. So let me just write the Kronecker delta k m minus the Kronecker delta j m Kronecker delta k l. Perfect. So this relation will be again useful on the next process. Okay, so what happens if we begin with the result that we just found? The Levi-Civita symbol I, j, s, omega s, and we multiply this quantity by a factor of a, r, j. Well, this will be equal to, as we saw, we have this relation, so we can substitute this quantity for this. So we are going to have that this is equal to A dot Ki Akj and then times Arj prime. Perfect. But look that we have the product of two components of the transformation matrix. And we showed, let me see, yeah, that is the Kronecker delta. Okay, so we are going to have here that this is going to be the Kronecker delta Kr, and we are going to get A dot Ki Kronecker delta Kr. So this is going to be, of course, A dot IR. And let me switch this RI like this. Perfect. So we have concluded that this quantity is equal to this quantity over here. That is the important result. And why is that? Because remember that on the kinetic energy term, we had the product of these quantities like this. Okay, so right now we are trying to express these quantities in terms of the omega term that we found. That will, you can see that it will represent the angular velocity of the rigid body. Perfect. So looking that we have the product of those quantities, well, we are going to start by calculating now, for example, how to represent the term Aj dot. Well, if we follow this instruction, we are going to have that this is going to be the Levi-Civita symbol ILS omega S times AJL like this. And for example, if we want to calculate the other term that we had, it is AJK dot. It can be set as the Levi-Civita symbol K N R omega R AJ N like this. Perfect. So what happens if we multiply these two quantities? Well, we are going to have that A dot Ji times A dot Jk is, well, let me copy these quantities to make it faster. Okay, perfect. We will have that expression over there. Again, we see here that we have a product of these quantities, and well, that means that we are going to get a Kronecker delta Ln. Okay, and we can operate that Kronecker delta with this Levi-Civita symbol. We see here that this will transform the Levi-Civita symbol to E or epsilon, sorry, KLR. Okay, this N will be switched to an L of the Kronecker delta. So that means that we are going to get epsilon I L S omega S and then omega R and then the Levi-Civita KLR. Okay, perfect, but look that we have the product of the Levi-Civita symbols. So here is where we are going to use the relation that we defined here. Okay, so we are going to get the next. This will be equal to the Kronecker delta S R Kronecker delta IK minus Kronecker delta S K Kronecker delta IR times omega S omega R. You can verify that this is correct. Okay, so what are we going to have next? Well, I think that for now this expression can be left as it is. Remember that we were calculating the product of these two quantities. Here is, well, that is equal to all these that we have. So we can go back to the definition of the kinetic energy, and we are going to substitute the result that we just found into here. Okay, so let me do that. Perfect. So this is what we will get if we substitute the result in the kinetic energy term. So what we are going to do now is to take these Kronecker deltas into the sum to multiply these xi and xk with these Kronecker deltas to see what are we going to get. So let me write this as t equals omega s omega r, the sum from alpha equals to 1 up to n of 1/2 m sub alpha, and then all this product of Kronecker deltas here times xi alpha xk alpha. Okay, perfect. So what happens if we multiply this with this? Well, first of all, look that this x depends on I. So it will be affected by this Kronecker delta here. And that will change this index to a k. Okay? Perfect. Okay, so we can write that. The sum from alpha equals to 1 up to n of 1/2 m sub alpha. The Kronecker delta is r times xk alpha alpha. You can see that that here we have the same components for x. Okay, so that represents the magnitude of the vector squared. It's like taking the dot product of the r vector with itself, like this. Okay, perfect. So okay, but let's make a pause on that step to see or to think what is going to happen with the Kronecker deltas that we have here. Well, looking that again, this x has the I index. It will be affected just by this Kronecker delta over here. So this index is going to be transformed to an r, looking that there is an r on this Kronecker delta. And this index k will be affected by this Kronecker delta here that will make this k2 to become an s. Okay? So we are going to have here minus xr alpha xs alpha. Okay, perfect. For now, we are going to change the r and the s for, again, the I and the j index. Looking that, well, it is the same, but just for convenience, we are going to use the I and the j again. And recall that these can be defined as r alpha, sorry, the alpha is here, and this squared. Okay, perfect. So we are going to have that the kinetic energy can be expressed as omega s, sorry, we said that we're going to change this. So it's omega I, omega j, the sum from alpha equals to 1 up to n of 1/2 m sub alpha, the Kronecker delta I j, r sub alpha squared minus xi xj, like this. Okay, perfect. So we are almost over. For now, we are going to define the inertia tensor as the 9 real numbers that are represented in the next expression. The sum from alpha equals to 1 up to n of m sub alpha times the Kronecker delta I j r alpha squared minus xi alpha xj alpha. And why is that? Well, remember that the indices I and j goes from 1 up to 3. So that means that we have 9 elements for this inertia tensor. That's why I said we had 9 real numbers. Perfect. So looking that we just defined what is the inertia tensor, well, we can just say that the kinetic energy of the rigid body is going to be equal to 1/2 omega I omega j times I. Perfect. And well, yeah, the book remarks that this inertia tensor is defined for the indices I, j. That's important, okay? So again, we will need to write this here. Okay, perfect. So that will be the formal definition of the inertia tensor for a rigid body, and the kinetic energy of that rigid body is given by this expression over here. Okay, and just to mention a last thing that will be very important in this topic is that we are taking into consideration that the rigid body has a discrete distribution of particles that compose the rigid body. But what happens if we have a continuous distribution of a mass that compose the rigid body? Well, we know that if we have a volume of mass density given by m over b, for example, looking at, well, the kinetic energy term involves the mass, we can express the mass as the density times the volume. Okay, but if we are interested in continuous distribution, we can express the inertia tensor as an integral. That will be the integral of the density of the distribution that will depend on the vector r that allocates the point where we are measuring the density, and then times the Kronecker delta ij r squared minus xi xj dB. Okay, this will be like making the change from the discrete definition to the continuous distribution. We just substitute the mass for the volume density of mass. Perfect. So yeah, this will be the final result of the video. Remember that again, I'm going to leave you the name of the book that I'm using to make these videos in classical mechanics on the description of the video.